Have you ever just looked up at the sun and wondered what's really going on up there? I mean, we see this bright light, we feel its warmth, but that familiar star is a place of just unimaginable power. It's the engine of our entire world. So today, we're going to take a journey to the heart of our star.
See, this is not some calm, steady ball of fire. It's the churning, boiling surface of a nuclear furnace. And what you're seeing is the direct result of the immense convection happening just below. Every single second, it converts millions of tons of matter into pure energy. So that's what we're going to do in this explainer. We're going on an expedition from this chaotic surface deep into the sun, all the way to its core, to find out how it really works.
But before we dive right into our sun, let's kind of pull back for a second. You got to remember, our sun is just one of an estimated 100 billion stars in our galaxy alone. It's part of a vast, vast cosmic family. It seems like a simple question, right? But the answer takes us into some of the most extreme physics in the entire universe. So what are these things, really? These celestial bodies that light up our sky? Well, at its most basic level, a star is a giant ball of plasma. And I know, plasma sounds all sci-fi and exotic, but check this out. It's actually the most common state of matter in the universe. It makes up over 99.9% of everything we can see. It's basically what you get when stuff gets so incredibly hot that atoms are literally torn apart.
And yeah, stars are definitely not one size fits all. This thing you're looking at, it's called the Hertzsprung-Russell diagram. Think of it like a cosmic census for stars. It plots their brightness against their temperature. You've got these scorching hot, bright blue supergiants up here, and these cool, dim red dwarfs way down here. And our sun? It's sitting right there, in that long band called the main sequence. That's the sweet spot. You know, the long, stable, hydrogen-burning phase where most stars spend the bulk of their lives.
And get this, stars aren't permanent. They have a life cycle, just like we do, but on a cosmic scale. They're born from these collapsing clouds of gas and dust called nebulae. They live for billions of years, and then they die. Some just kind of fade away as white dwarfs, but the really massive ones, they go out with a bang, a spectacular supernova, leaving behind neutron stars or even black holes. Our sun, for the record, is basically middle-aged right now, about halfway through its nice stable life.
All right, so now that we've got that cosmic context, let's zoom right back in on the star that matters most to us. You know, the one that makes everything here possible.
Let's do a quick fire round of stats just to give you a sense of the sheer scale we're dealing with. For starters, the sun is about 4.6 billion years old. The universe itself is about 13.7 billion, so the sun's been around for a while.
Its core temperature, a staggering 15 million Kelvin. If you're thinking in Fahrenheit, that's nearly 27 million degrees. Yeah, there's just nothing on Earth that even comes close to that.
What about its mass? Well, it's 2 times 10 to the power of 30 kilograms. That number is so big it's hard to even picture. But think about it this way. The sun makes up 99.8% of all the mass in our entire solar system. Everything else, Earth, Jupiter, all the planets, all the asteroids, we're just cosmic leftovers.
Yeah, it's pretty hard to wrap your head around numbers that big. So here's a good one. If the sun was hollow, you could cram more than 1 million Earths inside it. 1 million.
All right, expedition time. Let's peel back the layers of the sun and take a trip, starting from the outside and going all the way down to the very center.
Okay, so this is our map. We're not talking about the surface stuff like sunspots and flares. Our journey is going inward through the 3 main layers of the sun's interior. We're going to start in the convection zone, then pass through the radiative zone, and finally we'll end up at the very center, the core. That's where all the magic happens.
Now you've got to hear this. This is one of my favorite facts. A particle of light, a photon, is born deep in the core, but it doesn't just shoot straight out. Oh no, the radiative zone is so incredibly dense that the photon gets absorbed and spat back out over and over and over again. It's like a cosmic pinball machine. And this random walk can take, on average, 100,000 years, 100,000 years, just to get through one layer of the sun. So, after that incredible journey, we've finally made it. We're at our destination, the core. This is the sun's engine room. This is where all of its power is born. And this is where we find the secret to its power. The sun, and pretty much all main sequence stars, run on nuclear fusion. And let me be clear, that is the single most powerful energy source in the entire universe.
So down here in the core, the pressure and the heat are just so immense. They actually overcome the natural force that pushes protons apart. So you've got two hydrogen nuclei, which are basically just single protons, and they get slammed together so hard that they fuse. And when they do, they create a heavier type of hydrogen called deuterium.
Okay, so after a couple more steps, you get to this part of the process. Two helium-3 nuclei smash together and form a stable helium-4 nucleus. In that reaction, a couple of protons get kicked out to start the whole cycle all over again, and this is the key part. A tremendous amount of energy gets unleashed as photons. And those are the very photons that are about to start that epic 100,000-year journey to the surface.
Now, you've probably heard of nuclear power, right? The kind we have on Earth. Well, that's usually nuclear fission, which is kind of the opposite of what the sun's doing. Fission works by splitting heavy atoms, like uranium, apart. But fusion, what's happening in the sun, it smushes light atoms together. And get this, it releases 3 to 4 times more energy. It's way, way more powerful.
Okay, so we've journeyed to the core, we've seen how the sun works, but let's bring all this crazy astrophysics back home. Why does any of this matter to us, here on Earth? Think about it. Every single ray of sunlight that you feel on your skin, every photon that lets a plant grow, literally every bit of energy that has powered life on Earth for billions of years, it all started as a tiny fusion reaction deep inside the sun's core, ages and ages ago.
But the connection is actually even deeper than that. It's incredible. The very stuff we're made of, I'm talking the carbon in your cells, the oxygen you're breathing right now, none of that was made in our sun. It was all forged in the fiery hearts of much bigger stars that lived and died billions of years ago. I mean, it's not just a saying. We are, quite literally, made of stardust. So just think about this for a second. That little particle of light hitting your face right now, it just traveled 93 million miles to get to you, which took about 8 minutes. But before that, it spent the last 100,000 years just trying to escape the sun's core. That light began its journey before recorded history, before the last ice age. It's older than human civilization itself. Wild, right? Every star you see is like a history book and a physics lab, all rolled into one. And when we really dig into our own sun, we find a story that connects us all the way back to the beginning of everything. It just makes you wonder, doesn't it? If this is the incredible story of just one star, what other secrets is the universe just waiting to tell us?